We've learned the general theory of linear equations, and we looked at the reduction of order method, which allowed us to take one solution of a homogeneous linear differential equation and compute a second solution. Now we move on to computing solutions to homogeneous linear differential equations from scratch, with the important assumption that the coefficients of our differential equation will be constant. Okay? And now that may seem pretty restrictive, but in differential equations there are many subclasses, and the way you solve differential equations is by focusing on specific subclasses. In other words, there isn't really this general method of solving all differential equations. So you take what you could get when you work with differential equations. So let's consider the case of first order linear differential equations, homogeneous linear differential equations with constant coefficients, okay, where a does not equal 0. Now we know how to solve this. We could do it via separable equations. We could also use the linear equations method for first order differential equations and solve this. But for purposes of demonstration, let's take a different approach. Let's guess a solution, okay? And when we look at this differential equation, you could move this by to the other side. And what you're basically getting here is that the derivative of a function, y, is proportional to that function. Now we know what general function behaves this way, okay? The exponential function. So it's really reasonable to guess that our differential equation, the solution to it, has this form, okay? And that's precisely what we'll do. The derivative then of this general form will give us this expression here. And now we could plug these into the differential equation and factor out the e to the mx. Now e to the mx is never 0, so that means this expression here must be 0. And we get this equation here, okay? Now this is what's called the auxiliary equation. It's most famous in second order differential equations, but there's no problem with calling this the auxiliary equation. And we solve for m, and we get that m needs to equal negative b over a. This is telling us that we guessed correctly for our general form, okay? So we made the right assumption if, and indeed we do get a solution if m is equal to negative b over a, okay? And now any solution to a homogeneous equation, a constant multiple is also a solution. So we get a solution where we have this constant c times e to the negative b over ax. This is actually the general solution because it's a first order differential equation. So our fundamental set will only have one function. And so we just found our general solution to to differential equations of this form. So let's generalize what we did before, but for second order differential equations. And this is the main application for auxiliary equation, okay, in this general method. So we have a differential equation that looks like this. All the coefficients are constant, okay, as you see here, and a does not equal 0. We're going to guess a general form. Y is equal to e to the mx, okay? And so we get the derivative here, and we get the second derivative here. And we plug these into our differential equation. We factor out the e to the mx, and we're left with this equation here that will give us our restrictions on m, okay? And this equation here, it's very important, especially in second order differential equation. So we're going to define it, okay? For the differential equation that you see here with, of course, constant coefficients and a not equal to 0, the auxiliary equation of this differential equation is what you see here, okay? And so you just take the coefficient of, say, the second derivative, and you have this variable m squared, okay, the coefficient of the first derivative, and you have m. And notice the orders here are consistent. So this is m raised to the power 1, and this is the first derivative. This c is, this is the 0th derivative, if you will. And this here is m to the 0, if you will. Okay, so the orders are consistent. Well, in the case of second order, this is pretty straightforward to get solutions to this polynomial equation now. Notice that we've shifted now from a differential equation problem to a polynomial problem, okay, to an algebraic problem. And so we know how to solve this. We have the quadratic equation that you see here, and we get two solutions, with one with a plus and one with a minus. And there are three cases now to consider. The case where b squared minus 4ac is strictly greater than 0, so what's inside the square root is strictly greater than 0. Here you're going to get two distinct real numbers, okay? When what's inside the square root is 0, you get a repeated root. And case 3 is when what's inside the square root is negative, and there you get complex conjugate roots. And we will consider these three cases in their own right.